Good morning, class, or afternoon, depending on when you're waking up and you're getting to do this. I'm not going to do this every day, but I thought today would be a good opportunity for me to do this. It gives me an opportunity to kind of talk through a lesson and give you a little more well-rounded view of what we're doing, and kind of give you instructions on how you can go about this and give you some suggestions on how to best manage. These online transitions because it is tough. I'm not going to lie. Getting used to this can be very, very difficult. So, right off the bat, I just want to give you a couple options that you can do. What I have in front of me right now is I have the slides up here and I have the notes here. Both of these files are attached to the assignment when you come to do this assignment. What I suggest is that you have them up at the same time. If you're not on a computer like me and you can only really do one or the other at a time on your phone, what I suggest is you take the notes right here and you do these on loose leaf or in a notebook. Um, because taking notes is still a really important part of this lesson, part of this class, and it helps you remember things and helps you get that practice that you need. So whether you print these notes out and you do them by hand, or um, whether you decide to open them as a Google Doc and edit them this way, that's fine. I really, really don't mind. What I'm going to need to collect from you, unless otherwise stated in the assignment directions, is usually going to be the exit ticket, like usual in class. And I'm going to include directions later for how specifically to collect and submit just the exit ticket, so we're not doing more than we need to. So again, for right now, I'm going to go through this as though I'm a student going through the PowerPoint. I have the PowerPoint over here. I have my notes over here. You can have this in loose leaf as a printout on your computer, whichever option works for you. I'm not telling you how to do it. So, what we're going to talk about today is Boyle's Law, and we're going to go a little deeper into um, gas laws and a little stuff that we previewed yesterday. So, yesterday with the preview was ideal gases. And what are these overarching rules that we use to describe how gases behave? Well, there's a bunch of scientists who came up with these interesting laws about how ideal gases behave, and that's what we're going to talk about. Specifically today, we're going to talk about Boyle's Law and the relationship between volume and pressure. So right off the bat, we got this video. So if you click it, it should bring it up in a new window. And we've all seen something like this before.
Fail.
Delightful. Okay, so what happened there? Well, she was walking on bubbles, and when this woman steps on the bubble, she's changing the shape of that packing bubble. And when it gets too small, or when you shrink the volume enough, the bubble ruptures. That's all pretty obvious to think about. We think about when we have balloons. If you squeeze a balloon, the balloon pops. But why is that? Because gases are compressible. We can stretch them out into really big containers, or we can pack them into very, very small containers. But a lot of times we don't think about it as a relationship between pressure. So before we talk about pressure and the relationship between pressure and volume, we have to define what pressure is. So why did those bubbles pop? Pressure, by definition, is a force per unit area of surface. So anytime there is force distributed over a surface, there's pressure. Anytime things come in contact with each other, they exert pressure on each other. When we talk about gases, it's related to the number of collisions that the particles make with the walls of their container. So if you can imagine this is maybe a little steel box here, and we have gases, notice all of them moving in straight line motion like our ideal gas laws say they should. When they hit the walls of the container, they bounce off, and all these little red lines represent that. And anytime that something bounces off of something else, it's going to exert a force. So that outward force that these gases are putting on this container is the pressure of the gas. When you blow into a balloon and that balloon stays inflated, That's because the gas particles are bouncing off of each other and bouncing off of the walls of the balloon, pushing it outward. If you put more gas in the balloon, there will be more particles colliding with each other, increase the pressure, push the volume of the balloon wider. Makes sense. We all can imagine doing this because we've all done it. The force of all the gas particles bouncing off the walls of the container are what create the pressure to keep it inflated. So when we talk about the pressure of a container, we're talking about the average force of all of the particles bouncing off the walls. So when we talk about this in terms of volume, this first image we got right here is a few particles in a cylinder, and they're bouncing around. You see these little yellow markings where they're banging off the walls. Ooh, I forgot to mention, at this point, we should be doing our notes. Definition of pressure. It was just given up here. So I would either write by hand or type into here my definition of pressure. Right, sorry. Back to my example. When we have a few particles in a big space, they're not going to spend a lot of time bouncing off of each other or bouncing off the walls of their container. If they're not hitting the walls of the container, they're not exerting force on the container, the pressure is going to be low. What happens though if we just drop the ceiling of our container? We make it the space smaller. Now the same amount of particles are in a smaller space. I liken this to when we did this example in class where I had students pretending to be particles walking around the classroom. The more students we put into the classroom walking around, the more they bounced into each other and ricocheted off of each other. So makes sense. If you take the same amount of particles and we push them into a smaller area, they're going to have more collisions with the walls and with each other, and that's going to cause the pressure to go up. Instead of changing the volume, we can just put more particles in. So if we keep the volume large, but we just feed in a bunch more gases, we can cause the pressure to go up that way. More collisions on the walls, higher pressure. When we talk about units, and again, if I was a student taking notes, I would go over here and I would fill in these units over here. All of these units, just like we can use feet and meters to measure length, these all measure pressure. This is the one that we use a lot in the US and in weather. Pascals and kilopascals are your metric units, and torrs is also used in weather a lot, and you'll also see milliliters of mercury. I know you saw this in Earth Science last year with Mr. Myers. This is your standard pressure, 1 atm, 101.3 kPa, 760 torrs, and 760 millibars. You'll notice these are the same unit, just different value, or a different unit, same values. Easy scale. I know you remember from Mr. Myers doing millibars or millimeters of mercury. You'll see on your reference tables at standard temperature and pressure, this value is listed for standard pressure. So I just want you to be familiar with that term. When you see standard temperature and pressure, it just basically is saying under constant conditions. So let's make those conditions unconstant. I've been talking about a relationship between pressure and volume, so let's check it out. If you have this PowerPoint up in front of you, you can click this right here, and it will open up a link to this simulation. We're going to mess with the ideal gases. So let's mess with pressure and volume. I'm going to put some gas into my container. Notice we have a big space right now. And we're at 300 Kelvin. I am going to set the temperature to be constant. So now, whatever I change, it's only going to change the pressure and the volume. Temperature won't be affected. And we'll incorporate temperature later in this unit. So let's just see what happens if I take this and I shrink the box. Now we have the same amount of particles packed into a smaller area. Notice what happened to the pressure. Let's open it back up again. Whoop. Bigger box, same amount of gas, bigger box, lower pressure. Shrink it again. Smaller space, same amount of particles, more particles colliding with the walls, increasing the pressure. So I suggest that you open this up and you have a little fun with it. Go ahead and make nothing constant, mess with what temperature does, what speeding up the particles does to the pressure, what cooling down the particles and slowing down their motion does, what maybe adding in another particle could do. We're going to return to this simulation later in the unit, but I just wanted to show you this and put this in your heads. Go ahead and mess around with this, see what you can discover for yourself. So back to the PowerPoint. For those of you that did the introduction lesson yesterday, you will have already seen this video, so I'm not going to play it right now. Basically what happens is you boil a can of water with a little bit of water in the bottom, and then when you invert it and put it into a pot of ice water or cold water, it crushes instantly. Just at a snap of your fingers, it smushes down to a little can pancake. So that was kind of my hook yesterday, but this is a prime example of pressure and volume. When what we're doing is we're creating a difference in pressure. So when the atmospheric pressure is greater outside the can than the air pressure inside the can, it will smush it. Like when you have a plastic bag and you suck the air out of the plastic bag and the bag gets flat, that's because you're lowering the pressure inside the bag, and the pressure outside the bag is now greater, smushes it flat. So when I'm boiling the water over here, the gas particles inside the can are moving very, very quickly. This water is turning to a vapor, and it's banging off the walls of the can and creating a really high pressure inside the can, and a lot of gas particles are escaping out the top. So the pressure inside the can is much greater than what's happening outside the can. As soon as I flip it over and dump it in the water, that ice water turns all of that liquid water vapor back into water. So all that's left in the can is a very small amount of water vapor and a very, very small amount of air. So because we have less particles colliding with the sides of the cans, suddenly, now the atmospheric pressure is suddenly much, much higher, and it causes the can to crush instantly. I highly suggest you look up a couple videos of like container trucks collapsing after they've been washed, or sometimes train cars, like tanker train cars that carry oil, after they're cleaned out and they get their insides steamed out. Sometimes this same thing happens to them, and these massive steam tanks are compressed instantly. It's pretty cool. I would look it up. So we've talked about this quantitatively for a while, but we do have to do a little bit of math. Sorry. So let's look at this curve that I have right here. Basically what this curve is saying is that as volume gets higher, pressure will get lower. And as volume gets lower, way over here, pressure will get much higher. Well, what happened over here was kind of the opposite. We made the pressure go from when it was being boiled very high to when it was being chilled very low. And the volume collapsed. The volume went way down when we did that. So let's see what we can do here. All right. I'm going to get to this in a minute, but first, here. I made myself a little Excel spreadsheet that goes with this part of your notes. So I'm going to write in a little function here. If anyone's on Excel, you might want to try to set this up yourself. This cell equals this cell times this cell. There. So what we get here is, oh, let me just format this for a hot second, make it pretty to look at. Pay no attention to the people playing music loudly on the street. Apologize for that. Okay. So if we fill in this column here, you might notice as the volume is changing, pressure's changing, but pressure times volume is remaining constant. That's interesting. So if we assume this to be true, and we say, okay, well, if this times this has got to be 200, and this times this has got to be 200, and this times this has got to be 200, then maybe I should just continue on. So I'm going to go ahead and assume that all of these are going to be 200. And then 40 times what is 200? 40 times 5 is 200. And look what happened to my graph. 25 times what is 200? 25 times 8 is 200. Look what happened to my graph. Isn't that cool? 10 times 20 equals 200. Look at that. Makes sense. As our pressure increases, our volume is lower. When volume is higher, pressure is lower. So what is all of this bringing us to? When we change the volume or we change the pressure, the other component will adjust automatically. So we talked about nature and how nature is in a constant state of flux. When one thing happens, one thing responds. Things will either be spontaneous or non-spontaneous, or need an input of energy or an output of energy. But whatever happens, the opposite is happening somewhere else. So as we decreased the volume, the pressure increased. And if we decrease the pressure, the volume will increase. They're related to each other. And this relationship is what Boyle observed, the scientist, the great mind Boyle. And he came up with this same curve. This looks a lot like the curve that I just made on that Excel sheet. And Boyle came up with this law we call Boyle's law. And you could be graphing that on your own sheet if you decide to print this out, what I just did. But what we're about to get to is to this question. If pressure and volume are always directly related, then if we change one, we can predict what the other is going to be. So we have this equation, pressure times volume equals pressure times volume. And this equation is on your reference tables, on table T. Or not table T, it's the back page of your reference tables with all the equations. This equation is there. It's in there as the combined gas law equation. So it's a little hidden, but we're going to get there. Boyle's law is pressure times volume equals pressure times volume. The ones, pressure 1, volume 1, these guys right here, this is what you start with. Pressure 2 times volumes 2, that's what you end with. So if you know where you ended or you know where you started, you can predict where you're going. So in this problem, the pressure of 400 milliliters of gas at a constant temperature is 0.5 kPa. What is the pressure of the gas when the container is compressed to 25 milliliters? So there's our starting point, what we started with. Here's our end. We know we're going to compress the volume to, but we don't know what the pressure will become. I put a video of myself solving this problem in the end of the PowerPoint, so I'm not going to make you watch that here. You can click that and watch that on your own time. And your exit ticket is to Boyle's Law calculation problems. There are directions specifically for how to submit that, but basically your two options are answer the questions on loose leaf, take a photo, and submit it through the assignment tab. Your other option are click the Word document file that I have in the assignment tab, put your work directly in there, and then click turn in. When you open this file, you'll see an option that says turn in right up here. And you can just do your edits in this file and click that. So it's up to you whether you want to do it on loose leaf, print it out, do it by hand, and upload the photo, or upload the file directly. I'll leave it up to you, just as long as just as long as I get it. Okay, I hope this has been informational, and let me know if you have any questions. Thank you very much.